Myself, Piyush Patel, welcome you all to the first session of the day 4 of the ATAL FTP on Waste Technology, organized by Chemical Engineering Department, Government Engineering College, Bharuch. Today, we have with us Dr. Jayesh Ruparelia as a speaker for this session. He will enlighten us on the topic of industrial effluent treatment, recycle and reuse, a case study of steel industries. I would like to give a brief introduction of Dr. Jayesh Ruparelia sir. Dr. Jayesh Ruparelia sir is the professor and former head of Chemical Engineering Department at Institute of Technology, Nirma University, Ahmedabad. Sir has completed his PhD and MTech from IIT Bombay and BE from Gujarat University. His research, area of interest in research and teaching is sustainable development issue, application of nanotechnology, industrial effluent treatment, cleaner production, environmental management system, environmental impact assessment of industries, environmental audit, energy efficiency. Sir has also organized IST approved 3 training programs. Sir received the Best MTech Thesis Guidance IST IPCL National Award for 2 consecutive years. In 2017, he got the second prize, and in 2018, he got the first prize. Sir also received the award of for Best Teaching in Best Engineering College Teacher in Gujarat from IST in 2019. Sir also received the research project under the Young Scientist Scheme by DST Government of India. Sir also part of the expert appraisal committee constituted by Ministry of Environment and Forest Climate Change, New Delhi for environmental impact assessment of project requiring environmental clearance. Sir has guided 5 PhD students and currently guiding 3 PhD students. Sir also guided 20 dissertations and more than 60 BTech projects. Sir has also published and presented 50 plus papers in journals and conferences. So it is a very small introduction of Dr. Jayesh Ruparelia sir. Now I request Dr. Jayesh Ruparelia sir to take the charge of the session and enlighten us with uh, his knowledge. Thank you, sir. Sir, please.
Yeah, thank you. Thank you for brief introduction. First of all, am I audible?
Yes, sir.
Yeah, okay,
Yes.
thank you. Yeah. So first of all, I'm thankful to Professor Vaghela and his team, Professor Ramani, Professor Mangesh and all, for organizing a very good FTP on burning issues of the environment. Really, in pandemic time, as a teacher, we should not stop learning. Okay, so we should share the knowledge, we should keep on learning. And to achieve this goal, I think Professor Vaghela has taken a very right step to organize a FTP on the burning issues, that is the environmental issues. Okay, and I've just browsed through the entire program, and most of the particular lectures are there. It's from the various field, and I hope that all the participants gain lots of knowledge over there. And I also try to give certain new dimension to this particular issue. So let's start. Hope my slides are visible.
Yes, sir.
Okay, just a minute. Okay, so just a minute. Let me just start my So today's topic is industrial effluent treatment, recycle, and reuse. Typical case study of steel industries. Okay, so in steel industries, we'll see that how we can minimize the waste, and whatever the waste that is generated can be treated, partially treated, and then recycled and reused. Not only for the making the steel, but for making it several different products. Now, steel industry is a very unorganized sector, and that's why I have chosen this particular sector. If you take up this petroleum sector or fertilizer sector, any particular the chemical petrochemical sector, it's right now it's well organized. But still, the I can say that the steel sector particularly, it's totally manual operations are there, and totally unorganized sector is there. So waste generation is tremendous, and most of the time we observe that most of the industries, okay, chemical and petrochemical, the solid waste generation is bit low, and waste water generation is much higher. Here in steel industry, both are good, in a high quantity, in tremendous quantity of the solid waste also generated, and tremendous quantity of wastewater is also generated. So urgent need is required that research may be taken up in this particular sector, and some can say good outputs, okay, or particularly the new findings, okay, may help this particular steel sector to sustain and particularly the global competition. Outline of my talk is I will start with the overview of a particular uh, steel sector across the globe and across the India, what is happening. Then the manufacturing process of steel industries, waste streams from the steel industries which is generated, that we'll see. Then particularly the three major contributors, okay, slag, scale, and sludge. Okay, these are the waste streams generated from the steel sector. So how to can say tackle this, and first we'll define that what is the slag, scale, and sludge, and how we can minimize that. So we are going to use the 3R, okay, for the 3S. Now 3R is not unknown for the faculty members, those who are working in the environmental field. So all the 3Rs we try to utilize for the 3S, that is the slag, scale, and sludge. And then afterwards I will try to give my research ideas, okay, the research carried out in laboratories, in industries, in the surrounding area with my students, okay, and we'll see that how it can reduce this particular burden on environment from the steel sector. So I will summarize that particular part in the end. So I request all the participants, as and when they have any doubts, they can unmute and ask me. Otherwise, at the end, I have kept the proper timings for the question and answer session. So you can stop me anytime, or you can ask at the end. But in between also, I will ask some questions to the students or the participants. So they have to just respond. So starting with the global view. If you see the per capita steel consumption, see, unless and until we realize that
Excuse me, sir.
yeah,
Sorry for disturbance.
yeah,
Slide
please.
is not moving. It's only showing first slide.
Outline slide is also not shown.
No, no, no. Only first slide.
Oh, just a minute. I will stop sharing. Just a minute. Is it okay now? Hello.
Yes, sir.
Yes, sir.
Introduction slide is showing.
Outline slide right now. Introduction slide. Slides are moving or not?
No, no.
No, no, sir. Slide.
Just a minute.
Sir, please share the screen, not window.
Okay, just a minute. So, desktop window. And now,
Yes, now it is moved.
so this is the outline of my talk and introduction slide. Okay, I hope all of you are now viewing the introduction slide. Yeah, introduction slide is visible.
Yes, yes. Yes, yes,
Oh,
sir. Yes, yes.
okay, okay, thank you. Okay, so starting with the global view of steel industrial sector. So why we need to understand this particular sector, because it generates a tremendous amount of the solid waste as well as the liquid waste. And by looking at the global consumption of the steel and the trend, okay, not only the right now what is the consumption, okay, in India and abroad, but also what is the futuristic trend that we need to understand. If we understand that, then we can realize that, okay, so steel demand is going to grow. Simultaneously, if the steel demand is going to grow, we are going to have the large quantity of waste to be generated by the particular sector. So per capita steel consumption, okay, that is a strong indicator of nation's economic development. That is believed across the world. It is believed that which country consumes how much of can say steel, okay, per capita, that represents the nation's economic development. Now if we see the per capita steel consumption over here, okay, uh, and per capita steel consumption on y-axis and the x-axis we have the per capita GDP. So you can see this graph provides that India, okay, at 74.7, that particular point, okay, and other countries, okay, like China, South Korea, Italy, Japan, Germany, they are far ahead than this particular India. Now, government of India increase in the per capita steel consumption to 160. Now government's target, okay, by 2030, 2031, okay, from 74 to 160. So steel consumption per capita, okay, that much is going to increase. So almost double, okay, within a 8 to 10 years. Now this target, if at all it is achieved, okay, then also you try to understand that not only the steel is consumed, but the waste which is generated is going to be very large quantity, tremendous quantity will be generated. So we need to think about that, how we can just reduce the waste, how we recycle, okay, this particular waste which is get generated. So rapid rise in steel production in India, okay, that is for sure. Second largest producer of the crude steel since 2018. India is the second largest crude producer, crude steel producer, okay, from 2018 onwards. So India, we can say that right now on a growth trajectory. Now, when this growth trajectory started for the China, the same scenario was observed before 20, 30 years back. The China started with a certain small quantity and then still keep on steel consumption, okay, and steel consumption per capita keep on increasing, and simultaneously the waste generation also getting increased. India is the largest producer of the sponge iron or DRI, direct reduced iron, in the world. Second largest finished steel consumer in this particular world. So you can see that India is again in across the world in top three positions, top three ranks. Not only that, but particularly the growth trajectory is achieved, and government's target is that 2030, 2031, that this whatever the per capita is there, that's going to be per capita is going to be doubled. Okay. Now there is a high correlation between the GDP growth and steel consumption. Now, most of the countries, when we see that the GDP is increasing simultaneously without consuming this particular more and more steel, okay, per capita, this is not achieved. So, one way or other way, particularly the growth history of the various countries studied by the researcher, okay, and they have proved that particularly this steel consumption and GDP rise both usually go hand by hand. So why? Probably the reason is that infrastructure building phase is going on, and because of that, particularly this growth phase is achieved. So, for example, for the Korea and China, okay, in 1980, particularly in Korea, and 1990 in China, whatever the GDP is there, whatever the per capita steel consumption is there, okay, if both studied with respect to year, okay, can see that GDP increases simultaneously, the steel consumption also get increased. So both things are going hand on hand. Same thing is expected for our own country, India, that 1980, 1990, 2001. And you can see that after, can say 2010 or 2014 onwards, this growth trajectory started for India. And particularly the steel consumption and GDP both are increasing. So this data, all data is captured from this, particularly the Ministry of Steel. Joint Parliamentary Committee has prepared this report and then given this, particularly the one sort of warning that steel industry must be prepared for the, particularly the waste which is going, tremendous waste which is going to be generated in coming decade. Now, going for the detailed domestic view of the steel industry. Okay, you can see that capacity of this, particularly various, can say steel producing industries. Okay, which having these different technologies. Usually, we have this. BF or BOF, that is a blast furnace or blast oxygen furnace, okay, that represented with blue color. Okay, then electric arc furnace, that is represented with this particular dark orange color, and induction furnace, that is with the light orange color. So usually all the three technologies are used for the steel industrial sector. Now all these different kind of furnaces, okay, you can see almost equal weightage is there, 30-40% for each technology. They have their own advantages and disadvantages. We are not going in that detail because it's not a particular lecture on which technology is more suitable. But if you see across the India, okay, various part of the India, like for example in northern India, will find more electric arc furnaces. You can in eastern India will find more, particularly the BF and BF. There is a blast furnace and blast oxygen furnace. Western part also you'll find both type of technology. So this kind of particularly technology is adapted, okay, for the production of steel across the India. Not only this particular circle represent the type of technology, but this circle represents this size of the circle represents the capacities. Okay, so you can see that in particularly eastern side, okay, you'll get more capacities located, more capacity steel plants are located over here, and western part also, and some very few in particular southern part. Now, steel demand potential and economic growth potential, if we see, okay, that is prepared by World Steel Association, okay, for various states, okay, that low, mildly low, high, mildly high, and high. So you can see that particularly this economic growth and steel demand potential for this particular various states of the India. So you can see that some Assam, Sikkim having a very least demand, where Bihar, Jammu, Kashmir, Kerala, Madhya Pradesh, Punjab, Rajasthan having a particularly medium demand. Whereas industrial states like Andhra Pradesh, Chhattisgarh, Jharkhand, okay, where more, I mean, mildly high demand is there for this steel, as well as the growth potential is also there. And highly industrial states like Gujarat, Haryana, Maharashtra, Tamil Nadu, they are having a large demand of this particular steel. So highly industrial states also require the high capacity of the plants. I mean, particularly the steel demand is very high. Now, here you can see that industry is divided among the few integrated steel manufacturing and fragmented MSME steel players. Now, steel industry is a very typical kind of industry where you will find the integrated plants also from, I can say, raw materials, that is the ore, starting from the ore to finished product. So it's integrated plants. And you'll find the MSME sector, okay, medium and small sectors. Small and medium scale industries are there, which also plays a very good role in this particular steel sector. They usually engage themselves into the small finishing products or making a small fragmented units which recycle this, particularly the steel which is a scrap material, this that, okay. So they are also in both way these industries are working, MSME sector as well as the integrated large scale plants. Now, MSME steel players are lack of technical knowledge or technical know-how on the latest trends of the production and on 3R. Okay, so waste related issues are major. Okay, with MSME sector, integrated plants. Okay, they are capable. They can hire the engineers. They have the investment capacities. Okay, so that they can invest heavily on I can say waste recycle, reuse, or we can say reduce the particular environmental burden, whereas the MSME sector is lacking the knowledge and lacking the money also for this particularly the. So this problem is more persist particularly in MSME sector, and we can say that these industries are more polluting. Okay, no doubt they both are the steel sector, MSME as well as the integrated plant, but MSME sectors are more polluting compared to the integrated plants. Even today, we can see that in the last 3 to 5 years, the competition from the foreign players, especially China, increased tremendously. China started dumping the steel in India also. So this sector has very difficult time, passing through the very difficult time to survive. So Indian MSME players lose market on a global front, not only the domestic front, but they are losing the market on global front also. So if they are adopting the good know-how for the reduce, recycle, and reuse, probably they can take up this or this challenge, and they can compete not only in the domestic market but also in this particularly the global market. So this is what the making the background for this particularly need for this steel sector to be considered for this environmental perspective, generally for the integrated steel plants. So now this is a very good findings, okay, I got from the research papers, that for integrated steel plant, each ton of liquid steel needs about 2.8 tons of the raw material. Okay, so whatever the raw material required, okay, for production of each ton of the liquid steel, 2.8 tons of the raw material required, 2.5 tons of water, and 5 tons of air that is going to be consumed. So 2.5 tons of, so more than what per ton you can get, you can consume the two industries are consumed, and that is we are talking of the integrated steel plants, not the MSAP, because for that this kind of study is not carried out, and we are not having a approved or can say authenticated results. The outcome from iron and steel making process is 8 ton of moist dust, leaden gases. So 8 tons of gases getting generated, moist gases, okay, with a certain dust and other particles. 0.5 ton of effluent water, 0.4 to 0.8 ton of solid waste. Okay, so what happened that 0.5 tons, so per ton, 0.5 ton of effluent water getting generated, and 0.4 to 0.8. There is a huge variation because depending upon the various processes, various furnaces that is going to consume operated for the producing the steel, different quantity of can say this waste, solid waste that is generated in the range of 0.4 to 0.8. If you consider even the least, that is a 0.4, then also we can say that per ton 0.4 ton of the solid waste that is generated. Now all the faculty members are associated with this environment field, those who are participating over here, they know the fact very well that the solid waste is particularly the more difficult to waste compared to the even the wastewater. That wastewater can be treated and disposed of properly, it can be recycled and reused, but for the solid waste, if at all it is not particularly consumed, properly recycled, then there is only one final destination for the solid waste. Okay, can anyone tell what is the final destination of the solid waste? Any of the participant can unmute and answer, so we can have the proper interaction.
Landfill.
Sir, it
Landfill, very good.
finally it's for the dumping.
Very good. So it's a particularly going for the secured landfill. Okay. Now, if at all it contains the municipal waste, then I mean, you can say landfill site you can have, but a secured landfill must for the hazardous waste. And this waste, that is a 0.4 ton waste, that is per ton of steel that is generated, that is considered as a hazardous waste. Okay. So then we need to, if at all it is not properly recycled and reused, so it has to be disposed of properly. And again, there is secure landfill. Okay, it's not a treatment, it's simply a postponing the problem. We are postponing the problem for the next generation. So you can see again, I would like to go back to the slide and just give you the idea that total capacity, you can see over here, what is the total capacity in India? 125 million tons of steel production, 125 million tons. And What is the waste which is generated? You'll see zero point 0.4. We are going for not for the entire range for 0.4 to 0.8, but if you go for the least, okay, minimum waste which is going to produce, then also 125, almost half of this particular capacity. Okay, so that much waste is getting generated from the steel sector, and that is a solid waste. Okay, we are not much worried about the wastewater, because for the wastewater we are having lots of advanced technologies where the wastewater can be treated in efficient manner, and we can recycle and reuse it. But for the solid waste, it's going to consume the piece of the land for the indefinite time, and it's not a solution, it's not a treatment, it's ultimately a postponing the problem. So manufacturing process of the steel, let's have a quick look over here, the iron and steel manufacturing process, where we can understand that how and which stream are contributing for the steel generation process, waste generation process from the entire process. So this process usually we can divide into the five main points. That is iron making, steel making, continuous casting, rolling, and main products are there. Okay, so what happened that initially whatever the iron ore is there in terms of the pellets or other things, okay, that is fed with that iron ore, sintered ore, limestone, coke. Okay, so this is a very basic process, that iron ore, coke, and limestone we have to add into the blast furnace. So after adding into the blast furnace, we can generate this particularly the hot metal. Now hot metal is transferred into the basic oxygen furnace, that is BOF or electric arc furnace, and then we are generating the billet, bloom, or slag. Now these one process is completed. Okay, now as I talked about this MSME sector. Now MSME sector take up these billets, bloom, slab, and then they are going to make this different kind of products. And integrated steel plants, they are taking starting from the iron ore to the finished products like seamless pipe, castings, seats, okay, wire rod, etc. from the integrated steel plant. So MSME sector usually again take up this particularly this billet, bloom, etc. Okay, and then reheating or continuous casting can be done. Again melting it and then making, passing through the rollers. Okay, rolling mills are there, and then from rolling mill, different kind of rolling mills are there. Different kind of products are getting generated from the roll, sheet pipe, shape, bar, wire rod, plates, etc. So now from different rolling mill, different mechanisms, different I guess equipments are employed, and you can get the different kind of products. So on paper it looks very simple process compared to the complex chemical and petrochemical process, but it generates a tremendous quantity of waste. Now let's look in the further detail of this particular the blast furnace, because from where we are going to generate the basic stream of the waste. The coke is burned as a fuel to heat the furnaces initially. Right hand side you can see the image of this blast furnace with the different temperature zones are there, and different reactions which is carried out inside this particular blast furnace. Here we need to add the coke. Okay, the coke is burned as a fuel to heat the furnace. As it burns, the coke gives off carbon monoxide, okay, which combines with the iron oxides in the ore and reducing them into the metallic iron. So whatever the iron oxide is there, which is coming from this particularly the ore, with that the carbon monoxide has to react. Now carbon monoxide when reacts to this particularly, you can see this reduction of I process over here. 3CO plus Fe2O3 gives the 2Fe plus 3CO2. So it's a simple chemical reaction, takes place at the 700 degrees centigrade inside the blast furnace. Sorry. This is a basic chemical reaction in the blast furnace. It has the equation Fe2O3 plus 3CO gives a 3CO2 plus 2Fe. Now the limestone in the furnace is charged and is used as an additional source of carbon monoxide and as a flux. Okay, so limestone is added inside this particularly the blast furnace at high temperature along with this coke. Now this will work as a carbon source of the carbon monoxide, also work as a flux to combine with the infusible silica present in the ore to form the fusible calcium silicate. Okay, so whatever the silica present, because iron ore comprises of not the pure Fe2O3, which is required in this particular reaction. It has a lots of silica, and the silica in also different forms. So with particularly calcium, okay, from the lime, which going to combine with this silica and producing the calcium silicate. Without the limestone, iron silicate would be formed. Now, what is the main purpose to add the lime over here? Because if the lime is not there, this reaction is not going to fulfill. Okay, and iron is forming this particularly the iron silicate. Okay, at the high temperature, we need to stop them because we are interested in producing the pure metal, that is the Fe. So Fe2O3 must reduce to Fe, not forming the I can say iron silicate. So limestone, okay, facilitates this reaction. So without the limestone, iron silicate would be formed with a resulting loss of the metallic iron. So it's a loss of the metallic iron. Fe is lost, and then again it's going to be very difficult to recover the irons from the iron silicate. It's easy to recover iron from the iron oxide. So calcium silicate plus other impurities from a slag that floats on the top of the molten metal at the bottom of the furnace. So at the molten metal at the top and at the bottom, okay, we are going to have these different impurities are floating and settling down. Ordinary pig iron as produced by the blast furnace contains the iron about 92%. Now whatever the product that is produced over here, uh, chemical reaction that shows the pure Fe, but it is not a pure Fe. It contains, when we take out the product from this particular blast furnace and analyze, usually it observed that it contains the 92% of the Fe, carbon 3 to 4%, silicon 0.5 to 3%, manganese is 0.25 to 2.5%, phosphorus, and trace amount of the sulfur. These type of different impurities are there presenting in this particular whatever the bar that is produced, which bars or billets which we have seen in earlier slide. Let me show you the earlier slide again over here. So billets, bloom, slab, whatever that is produced, okay, this contains certain kind of impurities. So sometimes it has to be again remelted to purify it and then going for the rolling mill. So these particular things are very important to understand, particularly the basic reactions in the blast furnace. So we can understand the which kind of waste which is generated, and then we can think of that how it can be further recycled and reused, so that the burden on the environment can be reduced and sustainability can be achieved. Then this is a other different type of case of furnaces, okay, where the same reaction is taking place but different mechanism is there. Usually the blast furnace is very well can say adopted across the India, where the temperature different zones are there. Same thing can be achieved by these electric arc furnace also, where you can provide the power supply and directly trying to melt this particular the molten mass, and then this kind of slag and particularly the different kind of impurities getting generated. So this is the BOF process, this is the EF process, okay. These are going to have one and same thing. We have to react with this particular the coke, particularly the limestone, and the iron ore getting reduced to produce the iron. Okay, so just a minute, hold on. I would like to show you a small video over here for the entire understanding. Just a minute. Is it visible? Hope this
Yes,
video
sir.
is with. Yeah. Okay. Okay. Let me play it.
જર્નલમાં એ પછી પાછા સબ્જેક્ટના પેલા ચેપ્ટર વાઇઝ અસાઇનમેન્ટ અલગથી આપ જે ક્વેશ્ચન આપને એ અસાઇનમેન્ટના કે આજ ખાલી કરાવવાનું આજ કરાવવાનું જે પેલું એમાં લેબનું વર્ક છે.
Okay. So let's coming back to our, yeah. Okay. So now which are the types of the waste generated in a steel plant complex? The video which we have seen, that is for the integrated steel plant, starting from the mining to the finished product. But you have seen over there also that specifically whatever the steel products are which is produced, it is again and again reheated. Now when you reheat the steel bars, okay, it is exposed to the atmospheric air, and then what happens that in presence of oxygen, the oxide layers start forming on it. Now in finished product, it is not required, so we need to remove that. So for each processing, lots of solid waste is scrap material. It's not a pure steel scrap. Try to understand. It's a different kind of waste which is generated and that is removed. Now, this is we have seen for the integrated steel plant, but the same process, and we have seen that in this integrated steel plant, lots of automation is there, so that we can save the energy, we can save the material, and the waste minimization also can be achieved. But when these manual plants are there, the quantity of waste generated is going to be much more higher compared to this integrated steel plant. So in steel industry, all the three type of waste materials are generated, that is the solid, liquid and gaseous waste. The generation quantity of the various types of waste materials differ from one steel plant to the other. Okay, so it's vary from the process to process, and if at all the two different industry adopting the same process, then also the different just like hot metal pretreatment slag. Okay, so these are typical type of the slag and sludge which is generated. One is the hot metal pretreatment slag, then dust, then GCP sludge, then mill scale refractories, scrap, muck, debris, etc. Then liquid waste like industrial effluent, oil, grease, etc. And gaseous waste like the flue gases and fume extraction. The major issues with the steel industry is the solid waste. Further, the solid waste disposal and dump are very big issue for the environment today, and therefore this waste are being tried for the reuse through the recycling and the utilization. So whatever the slag and sludge which is generated, that always require typical type of I can say treatment, or you can say attention, so that it can be further utilized or recycled. So summarizing the all waste streams, typically the solid waste and particularly the this sludge and scale. Okay, in this right hand side, this particular diagram, what happened that the raw material is there that is fed into the electric furnace, electric arc furnace and blast furnace. Now, when you send this material, raw material to electric arc furnace, the advantage is that you can directly go for the secondary refining. The LD converter is not required. But when you go for the blast furnace, you have to have one more processing step, that is the LD converter. But you can see that at the end of the process, before going for the secondary refining of the steel bars, which is produced, large quantity of the steel bars we have seen that can be lifted up by the cranes. This slag and dust that is produced, and that is known as the EAF, electric arc furnace slag and dust. Whereas on this process, we have the slag, sludge, and the dust that is going to be produced. Then secondary refining is there, because why here we have seen that at the end of the first process, we are going to get the 92% of the iron in the particularly the large bars or large modules, which is produced from the steel, from the raw material. So 92% of the steel is there. We require secondary refining to produce, to purify the steel in the further processing. Then we have the steel casting, then hot working, and then cold finish. This secondary refining after continuous casting is there, where the mill scale that is generated. Now mill scale from the hot working also generated. Then from the cold finish, that is the last process. Then we get the products. So from the cold finish, we are going to generate the mill sludge. So major issue is the slag from the blast furnace or electric arc furnace, then mill scale, and then mill sludge. These are the three things getting main waste stream getting generated. So in casting and rolling mills, waste material accumulated, which knows is the mill scale, 25 to 40 kg per ton of the steel that is produced. So okay, so per ton 25 to 40 kg of the mill scale that is produced, and mill sludge is a 12 kg per ton of the steel that is produced. So here you can understand that per ton this much amount of the waste inevitably going to be generated. Then mill scale is a generic and broad term given to the solid byproducts produced during the continuous casting, reheating and forming process of the steel that predominantly contains the elemental iron and oxides of the iron, such as the wusite, that is FeO, hematite, that is alpha Fe2O3, and magnetite, that is Fe3O4, as well as the oxides of various alloying elements, because you know that steel contains various kind of different material like chromium, manganese, etc. So their oxides also bound to happen, but bound to be present over there. So here in steel, when we are putting up this additional material to packing, because this is a final product, So here secondary refining process, we need to add the other metal also, so that we can have this particular final product ready, like stainless steel or very special purpose steel like. So different kind of alloying elements are there, and different kind of oxides of these alloying elements also present in this mill scale. It is estimated that over 13.5 million tons of the mill scale waste were being produced annually, translating about 2% of the global steel production. So what are the global steel production is there? Out of the 2% of this mill scale is generated. And that figure comes out to be the 13.5 million tons. So it's a very big amount, huge amount is there. That is in terms of the solid waste which is getting generated. The total iron content is normally in the range of 70%, with traces of non-ferrous metals and alkaline compounds. Now, in mill scale, if you analyze, okay, you can observe that 70% of the, you can say, iron is there of this mill scale, and the remaining is the different kind of particularly non-ferrous metals and alkaline compounds are there. These 70% waste containing, which cannot directly put into this furnace. If you put in the particular furnace, it is not going to give these particular results. Okay, so it is not so easy that mill scale can be directly put, because it contains 70%. Then we can directly put with this electric arc furnace or blast furnace. Mill scale is a totally different kind of waste. No doubt it contains the high quantity of this particular iron, but typical reducing environment is required so that it can be converted into the iron. So scientists are working across the world on this particular issue, but very few success are observed. Even not only this different kind of I can say oxides, but the alkaline compounds, lubricants, oils, and grease also present. Okay, in this particular mill scale, and that's why it can directly not utilized in this blast furnace or electric arc furnace. Okay, as a raw material. So this will give you some idea that where the waste material is getting generated. Typically, the solid waste material getting generated from the flow sheet of the steel making plant. See over here, it's one of the MSME, small and medium scale enterprise, where the steel rolling mill is there. It's totally manual operation. This furnace is over here, you can see, and from furnace they are putting up this kind of bar inside. Once it is become red hot, it is taken out. So you can see that this red hot bar is there, that is taken out. Now, as I told you that when we heating up again and again this particularly bars, okay, or billets, why we need to heat up? Because we need different products, different shape products. So like we require the seat, we require the pipe, we require the thin wires, we require rods. Okay, so different kind of products are required. So for that, again, we have to process this particular steel billets or bars. Now, when we heating up again, because once it heating up, it is passed through the rolling mill and we can have different kind of products. So when this bar become red hot inside the furnace, you can see that black color oxide layers start forming, because this particular red hot steel in contact with the atmospheric oxygen, and when it is in touch with the atmospheric oxygen at a very high temperature, oxide layers start forming on it. So this is the oxide layer that is formed. You can see these oxide layers are there. Now that oxide layer needs to be removed. So when it's passing through the rolling mill, this is the background. You can see the rolling mill is there, and you can see that one big red color, red hot bar is there. It is passing through the roll. So when it passed through this roll, okay, this particular black color oxide layers, whatever is there, is spill off or is just scrape off. So this again collected, and then you can see it looks like this. So it's a mill scale. It's a mill scale waste. Okay. So this mill scale which is generated, and you can have the piles of or you can say lumps of or heaps of the particular mill scale generated in a different industry. Now there are no takers for this particular this mill scale, and that has to be usually, you can say, particularly sent to this particular landfill site if at all proper takers are not observed or proper recycling and reuse techniques are not available. So 3S, okay, for like slag, sludge, and mill scale, which is generated from the solid industries. So the steel industry generates the 3S, okay, 3S, that is the solid waste streams, the slag, sludge, and mill scale. So you can see the slag looks like this. Okay, that is directly taken out from the blast furnace. Sludge, okay, that is usually from the particularly the ETP plant. Okay, and from that whatever the solid particles that is settled down from the primary treatment, okay, that is a sludge. Okay, that is taken up, and this mill scale, I have told you very clearly what is the mill scale in the previous slide. Okay, this is a slide from where the mill scale is getting generated. So slag from the blast furnace, sludge from the ETP plant, and the mill scale from the processing plants that is generated. Now, if you just look at this slag, sludge, scale, etc., their composition, okay, you can see that iron composition is 46% over here, FeO 18% to 21%, Fe is 51.8 percentage. Okay, so you can see that iron content is very high, almost about 50%, 40% that is observed. But along with that iron, we can have the lots of different impurities, and that too in a very high amount. So that impurity needs to be removed. Okay, then and then pure iron can be achieved, and that can be recycled. Otherwise, the recycling of these particular slag, sludge, or mill scale waste, okay, is very difficult. You can see on right hand side one more table is there, gives the idea about that list of solid waste with their sources of the generations. Okay, so these are the various processing of the processing units of the steel industries, okay, that we have observed over here in the earlier this flow sheet of this particular steel making, or even earlier in the video also we have seen different kind of processing plants. So from where we can generate different kind of the waste. Okay, so now different waste is there that require different treatment. It's not that we can mix all together and have different one specific treatment for that. Even industry to industry, the composition of chemical composition of this slag, sludge, and mill scale is also changing, varying. So we have to devise a specific treatment. Okay. Now for these 3A's, we have to go for the 3R. Okay, means reduce, recycle, and reuse. Okay, first and foremost, if we can reduce the production, then it is going to be very useful for us, because we know, being an environment engineer, that this 3R plays a very vital role in the sustainability, in the sustainable environment, sustainable world. Because without 3R, okay, because we need to consume the product, but if it is not passing through the 3R terminology, 3R technology, then it producing the tremendous amount of the waste, and that is not good for the our mother earth. So why 3R? The major three advantages of the recycling and utilization of waste, that is the economic advantage is there. Then we have the saving of the raw materials, conservation of the resources, better and cleaner environment, reduced cost of the disposal, conservation of the energy. It strengthens the laws that is made by the government. Okay, and then it I can say particularly motivates the industry, okay, to taken up this particularly the 3R technologies, okay, adopt it, and then least pollution should be there in surrounding area. Then community relation and public image of this particular industry also going to be improvise, okay, after this adopting the 3R technology. So there are several disadvantages of this 3R technology, and steel industry has to taken up this particular 3R technology. So certain can say minimization measures, okay, taken up by this particularly the various unit. So let's start with the BOF and EF, that is the blast oxygen furnace or electric arc furnace. Which are the waste minimization measures are there? Okay, you can see over here BOF SOP, okay, avoidance of overblown metal. Okay, so if you provide more oxygen, overblown metal, minimization of the fines in the flux mix, avoidance in the late addition. So proper time addition is required. What are the fluxes are required? Fluxes in terms of the limestone and a different kind of I can say chemicals which reduces the iron oxides into the iron. So different fluxes are there. Okay, that is to be added over there. Coke and limestone is the major flux. Then elimination of the zinc coated scrap in the burden, use of the optimum top blowing rate, pressure and time in the conjunction with the bottom blowing rate time, use of the low silica, okay, in hot metal, use of the low SiO2 silicon dioxide, etc. So this is a very important concepts that is come out from the research, that if you utilize this kind of you can take up this kind of measures, then the least amount of the sludge, slag and scale can be generated. Same thing for the electric arc furnace also, that minimization of waste at source through the improvement in the process operation and maintenance, such as the continuous charging. Okay, so you have to adopt for the continuous and not intermittent charging. We have to go for the continuous small quantity of charging continuously happening, so that this reaction is going to be continuous. Lime addition is a part of the bucket charge, contrary to addition by pneumatic addition or injection. So whatever the lime addition is there, it's with bucket. When bucket is charged with this particular the coal and ore, with that only lime should be added, properly mixed and added, not the separate addition is required. Adoption of the foamy slag practices to optimum extent, minimizing the carbon blowing by maintaining not so high carbon opening in the particular bath, providing the adjustable speed drives, ASDs, big house fan to reduce dust emission by 2 to 3%. So it provides the various means, various measures by which we can reduce this, particularly the waste, solid waste which is generated from this particular process. Now you can understand that these all things are related with the particularly the fine tuning of this operation. Now if at all it is an integrated plant, then you can fine tune with the various sensors, various equipments, various instruments. Okay, that is possible. But in a manual plant, okay, or MSME, okay, small and medium scale industries, this kind of automation is not there. Because of that, large quantity of waste is generated compared to the integrated plant. Even you can see that slag generated in the electric arc furnace, that is a improved charge mix preparation, cost effective optimization of the charge mix, maintaining the minimum basicity. Okay, so because we are adding the particular alkaline material, that is lime. Okay, so proper basicity should be maintained, but then basicity should be properly controlled. So that you can see that entire idea is of about the skill based operation. Okay, and if you look at the steel industry, hardly you will find a few mineralogists or chemical engineers are working over there, or environmental engineers are working over there. Most of the, you can say, unskilled workers are working over there, and because of that the large quantity of waste is generated. Now if you look for the waste utilization, this is about this particular reducing the waste generation. So in MSME sector this is hard to achieve, integrated sector you can achieve it. Now, when we are talking about this waste utilization, the first and foremost is the slag. The phosphorus content of the this BOF slag is too high to be used in iron making and steel making process. So this blast oxygen furnace slag contains the high quantity of the phosphorus. In the process of iron making, the complete phosphorus enters into the metal phase, which increases the load of phosphorus in the steel making process. So research and development supports that development the ways of the recycle the BOF slag in the steel making and iron making process by reducing the phosphorus. So by any of the way, if it can be reduce the phosphorus in this particular slag, okay, the utilization point can be very easy, because steel, or you can say the iron content from the these three A's, that is scale, slag and sludge, okay, more than 50%, but we cannot directly utilize or directly recycle in this steel making process. The reason is the simple, that it contains the manganese, chromium, phosphorus, calcium, silica, different kind of oxide, different kind of fused materials, and it prevents the direct recycle of this particular steel, okay, as this waste into the steel making process. And now one of the technology, there is the slag or atomization. The new technology of the atomizing molten slag is an innovative process that produces the high specification products with the multiple uses. This is slag atomization process is there, which is again is very costly process, and integrated steel plants can adopt it, but the small scale plants cannot adopt it. Slag atomizing technology is a process that converts the molten slag at around 1300 to 1350 degrees centigrade into the small spherical balls. This is known as the precious slag balls or PS balls. Precious slag balls or PS balls with a diameter range of 0.1 to 4.5 mm. The process consists of a high-speed air blowing system with catalyst and water exposed to the stream of falling molten slag. So what are the molten slag is there? So again, whatever slag is generated, that is to be molten at a high temperature, around 1300 to 1350 degrees centigrade, and exposed to the stream of the this catalyst and water. So with this, in presence of catalyst, water, and of high temperature, these molten slags, okay, produces these small spherical balls. That is called the precious slag balls. The PS ball structure is typically a stable spinal structure that induces the superior physical characteristics to the balls, and PS balls are classified by the size through the saving machines. So this is a picture of the sorry. This is a picture of these PS balls. On right hand side, you can see the slag atomization machine. The process described in the previous slide, that is followed inside this machinery, and then at the end you are going to get this slag atomization PS balls. So slag atomizing technology is a multi-function, multi-application system, a great managerial approach to solve the environmental and technical problems inherent in a waste material. It is going to be very costly, but it solves the environmental problem of this particular slag. SAT, that is slag atomization technology, is a strategic approach to overcome the environmental problems of furnace slag, where molten slag is immediately converted into the environmental friendly PS balls as soon as that is going to be dumped into. So it's an additional process. From the blast furnace, when the slag is generated, the slag is directly fed into the slag atomization machine. This is a blast furnace. From blast furnace, water slag is directly dumped over here. Yes, any of the faculty can say which number you can see. Just I would like to interact. I am not alone in this conference, this FDP. Which number is visible to you? Yeah, thank you.
Two number.
Okay, thank you, thank you. Now, second utilization point is the rail blast. Okay, so steel slag is hard, dense, and resistant to the both attrition and abrasion. Okay, it is a very inherent property that is resistant to the attrition and abrasion, and that is suitable for the railway ballast aggregate. So slag has technically been found suitable for use in a rail ballast. Steel plants started developing the infrastructure for crushing and sizing facilitates so that the sized material can be supplied to the railways as a rail ballast. So we can save this because ultimately once you have this kind of waste material in front of you, you require the proper place where we can dispose of, or we can reuse it or recycle it. Now this ballast material you are using from the stone material, okay, then what happens that you need to just dig up, you have to go for the mining, okay, and then upper crust of the environment getting disturbed, okay. So better not to go for the mining and utilize this waste material as the particularly the ballast. This research is also going on for this particular road and pavement material. So this pavement material is there, okay. So if you want to go for the road and infrastructure building up, okay, for that part we can use this slag. So slag has already been successfully used as a road making aggregate in steel plants in the place of the stone chips. Roads have been constructed inside the plant for heavy duty purposes exclusively with slag. Now here the one more important issue is that when we are using the slag as a particular material to making road or ballast, we need to check out that whether the leaching is there or not, because this contains lots of heavy metals, chromium, manganese and other phosphorus, so many things are there. So leachate study also needs to be carried out. And then second thing is from the civil engineering perspective, we need to check for the strength. So whether it is going to serve the purpose or not, that is very important thing. So on the comparison, it is found that it is better material than the stone aggregate. Here for this particular slag, it is observed for making the road, it is better than the stone aggregate, that is observed by the scientists also. Then rock wool is also produced from this particular the blast furnace slag. Okay, so rock wool usually used for, can anyone tell which application it is used? Rock wools.
For insulation, sir.
Yeah, very good. So it is used for the insulation purpose. So blast furnace slag and other material are either heated and remelted in a cupola or electric arc furnace at 1500 to 1600 degrees centigrade. Now, being removed or after being removed from the blast furnace, the molten slag is kept at the approximately the same high temperature and is allowed to flow out of the from bottom of this particular furnace. Okay, the molten slag is then blown to form the fibers by centrifugal force or similar means. Okay, so here we have the electric arc furnace, or you can have this particular smelting furnace. Okay, and then melting furnace. From that, this fiber production. So whatever the slag is there, that is blown out of that at the particular that high temperature only by using the cyclones. The fibrous rock wool is collected in a collection chamber. After this particular collection, you can use this packaging, and then you can have this different utilization point like insulation purpose. Even this slag, okay, civil engineers tried to utilize it for the cement making because it contains the calcium, it contains the silica, it contains the iron. So if by proper modification it can be utilized for the making the cement, then it is going to be how the better utilization point. So this slag is used as a cement making material for replacement of the clinker. Blast oxygen furnace slag act as an activator and gives the better strength. The presence of phosphorus results in a corrosion of the reinforced material in concrete structure. Now here the main issue is that P2O5 that is present. Now for reinforcing purpose, all of you have seen that cement slabs or cement concrete slabs or cement materials which is produced, okay, the steel bars are kept inside for the reinforcement purpose. Now presence of phosphorus, okay, is going to have this corrosive, creating the corrosive environment. So this prevents for the direct utilization of this particular the slag into the cement making. But if the P2O5 content is very less, okay, so while manufacturing this steel only, if you have maintained the proper content of the phosphorus and then maintain the least amount of the P2O5 in the final slag, then it can be easily used. If only 10% slag is used for cement making, the P2O5 content will be increased around 0.3%. So what particularly the these cement making industries are doing, okay, they are taking up the slag, okay, and mixing, and they are utilizing the very limited amount of the slag, so that the final amount of the P2O5 in the final product is 0.3%. Okay, so around 10% of slag is they are utilizing, and remaining is the original material. So by using that, they are consuming the least amount of the raw material for making the cement. So these P2O5 content, if at all it is less than 0.3%, which is not so harmful for the Portland slag cement, that is the PSA. So usually the common cement we know as a Portland cement. So for that 0.3% of the phosphorus is allowed, and companies are maintaining that particular level. National Council for Cement and Building Materials, where SMS slag is proposed to be used as the raw material for the production of the ordinary Portland cement and admixture in Portland slag cement. So either as a raw material or either as an admixture, this slag can be utilized. That is approved by National Council for the Cement and Building Material. No doubt certain changes are required, certain things are required. Now in one of the scientific paper I found this cement water ratio with compressive strength. Okay, so this is a traditional concrete. You can see this blue color line, dotted line is the lower bound of the traditional concrete, and this is the upper bound of the traditional concrete. So for concrete which is to be having the certain compressive strength, okay, it should be fall inside this lower bound and upper bound, then and then the cement is considered good quality. Now whatever the slag that is utilized as a admixture or as a pure raw material, okay, from different industries, the steel slag concretes, okay, fall between this lower bound and upper bound, and hence it is proven that that can be directly utilized in the cement making industry for the and replacing the raw material, saving the raw material. This is one of the I can say very important aspect of the waste which is generated, that can be reused and recycled as the industrial cement making industry. Then brick manufacturing is also possible. SMS slag fines can be used in developing the bricks. Even the SMS slag mixed with the fly ash. Okay, what is the fly ash? Okay, can any of the participant can unmute and answer, please? What is the fly ash? Any of the
Says
participants?
it is the burnt material which is generated from the furnace.
Yeah, and usually from the coal fired power plants are there. Okay, so when the coal is burned, okay, this flies is getting generated. So this flies, okay, again it's like a havoc on the environment because a large quantity of flies is getting generated by collecting through the various means, the bake filters, cyclone separators, or electrostatic precipitators. We are collecting all the flies. But what is to be done with the flies? It's a big problem. So mixed quantity of this slag as well as the fly ash, okay, that can be making this brick. Okay, so scientists and researchers tried to make the bricks and they found very good results. Okay, with the various proportion of the slag and the fly ash can be mixed, and then brick can be manufactured. Now when you replacing the raw material of the brick, because raw material of the brick is the simple clay, so simple clay is the upper crust of the mother earth environment. So if you are replacing the particularly the clay by this waste material, then it is going to be very good utilization point for the waste material. Then it is also proposed that it can be used as soil conditioners. Crushed SMS slag of the size approximately 300 mesh size can be used for the soil conditioning. The soil can be corrected for its pH by suitably and adding the limiting agent, including the slag. The basicity of the slag makes it good liming material for the acidic soil. So once the identify that the soil is acidic one, okay, and now this slag contains the lots of limestones, okay, and other basic material. So if at all it is mixed with the soil, so acidic soil can become a basic. No doubt there is a warning sign that it contains sometimes the phosphorus, chromium, manganese, different kind of the material. So if these different kind of materials or metals are having a least quantity, okay, then we can go for the soil conditioning, or we have to utilize this material as the soil conditioning in a limited amount, so that the chromium and other heavy metals, okay, chromium, manganese, that quantity cannot be increased by the certain level, and then it is not going to adversely affect the soil. Phosphorus in the slag act as a nutrient, because in earlier we have seen that the phosphorus in the slag act as a corrosive material, so it prevents. But here for soil conditioner, the high phosphorus content is good because it works as a fertilizer. You know that fertilizer contains the three major compounds, that nitrogen, phosphorus, and potash, NPK. Okay, so if the phosphorus is available by these means, it saves this particularly the fertilizers, okay, and it conditions this particular soil. However, the SMS slag is required to be ground to very fine size for this particular purpose. The conventional grinding techniques are energy intensive. It is therefore necessary to develop a commercially viable crushing and grinding facilities for extensive use of the material as a soil conditioner. Okay, so here one of the research I found that the tea and coffee plantations are used for this soil conditioner, particularly the slug as a soil conditioner in a tea and coffee plantation, and gave the good results also. So there are basic you can say reactions how the soil slag fertilizer is going to help. So silica is there, Fe is there, calcium is there, phosphorus is there, manganese is there. Only thing is these all work as a micronutrient. Only thing is that is a chromium that is not required, but sometimes the chromium available in slag of this particular steel industry is very less. If the chromium is very less, then that particular slag is very much useful or very much having the potential for the utilization as a fertilizer or soil conditioner. So rest of the material is good for this particular soil for the plants except the chromium. Rest of the material is there, that is presented over here, and that is good. So that we need to understand that based on the chemical analysis, that where this slag or particular waste material can be utilized. Then another utilization point is the tiles manufacturing. Okay, so whatever the EF slag is there, okay, then you can ground it properly in the powder form, then mix with the clay. Okay, so both can be mixed properly, and then at a high temperature, okay, you can have the ceramic tiles. The ceramic tiles are studied by the scientists by various means. Okay, water absorption capacity, porosity, shrinkage, bulk density, etc. XRD analysis carried out, microstructure analysis carried out, leaching assessment also done, and then they found that it's going to give this particularly floor tiles. Okay, it's a good abrasive material property. So this mixing of slag with the simple clay. So here also we are going to save the raw materials. So earlier it is directly made with the clay only. But if I am mixing with this EAF slag, electric arc furnace slag, then it is going to give the better quality of the tiles. Then this
Sorry to
abrasive,
interrupt you, sir.
yeah.
Sir, can you again elaborate what is EF?
Electric arc furnace, electric arc furnace slag.
Okay.
There are two
Okay,
major
sir.
technology. One is the BF, there is a blast furnace technology, and electric arc furnace technology that we have seen. So from that, whatever the slag is generated, that is somewhat different, okay, compared to the blast furnace. And here it can be utilized for the tiles manufacturing. Is that clear?
Yes, sir.
Okay, thank you. Then abrasive blasting material. So SMS slag is the form from the precision balls, etc., having been successfully used as abrasive blasting material. So blasting is done. Okay, usually you heard about this ship breaking yards. Okay, I mean ship breaking yards, what they'll do, they try to recycle the steel, but this steel of this ship, okay, that is covered with a lots of paints and coatings. Now that paints and coating must be removed before the recycling of the steel. Now for that they require the blasting, proper blasting guns are there, and they are blasting this abrasive material, okay, on this surface of the particular ship or whatever the pieces of the ships are there, so that these paints and coatings can be removed. So once this paints and coating is removed, then steel can be going for this further recycling. Now this abrasive material, blasting material, okay, for that this slag can be utilized. That is one of the point, because it is having a very good abrasive properties. This slag contains the oxide of aluminum sometimes and iron oxides also, so that can be utilized for the water treatment media. Okay, if doesn't contain chromium and manganese, then if it only contains the aluminum and iron, then it can be utilized for this water treatment media also by utilizing the pH and other means. Okay, so slag filter is there, that is utilized in many research. I found that they have utilized it successfully, but provided that other impurities are not present. Briquette and micro pellets manufacturing. These are the produced by mixing the slag after metal recovery in the combination with the other solid materials like dust, sludge, and lime. So we can recover up this chromium manganese kind of the material, okay, from sludge or slag, and then we can make this particularly briquettes. Now this can be utilized for the supporting media in various chemical and petrochemical processes. These wastes are agglomerated by the mixing them in a definite proportion with binders to produce a combination of briquettes and micro pellets. Now there's micro pellets of briquettes having a very good abrasion and a very good temperature resistant properties. So it can be utilized as a particular the catalyst support in the chemical and petrochemical industry. There are multiple utilization is there. The micro pellets are of the size of 5 to 6 millimeter with adequate strength and chemical composition suitable for the sinter making. The briquettes can be used as a valuable source of the coolant in BOF, there is a blast oxygen furnace steel making. So these also can be used as insulating material because it is very highly porous. So it's used as a coolant also in the various processing to cover up the large equipments by these briquettes and micro pellets, so that the heat cannot be escaped and that can be confined in the particular equipment only. So these are being developed as an important means of the internal recycling of the solid waste in the steel plant industries. So steel industry is working on this and they have developed this kind of material. Okay, any of the participant can see which kind of which number you can see over here. Simply interaction for with you. Right now I cannot see the list of the participant, otherwise I can call by name. Which number?
3316.
3316.
Yeah. Okay. Thank you. Okay. So I am not alone in FDP. Thank you very much. Okay. Coming to this waste utilization again. So now going for the scale and sludge, mill scale and mill sludge. In an integrated steel plant, portion of the mill scale, the large size ones was recycled in sintering plants. Okay. But a study of recycling mill scale of steel in the sintering process showed that the sinter productivity decreases with the increase in the mill scale addition due to the decrease in the sintered bed permeability. Okay. So in the past years, steelmakers used this mill scale as an oxidizer in a conventional electric arc furnace. Now the mill scale is a very difficult to utilize. Okay, where to utilize this? Still the scientists are working on it. If they are mixing with the certain material sludge, the permeability reduce and then cannot be utilized further. So what scientists identified that it can be used as an oxidizer in a conventional electric arc furnace. However, the modern electric arc furnaces are equipped with the oxygen lensing system to enhance the melting and oxidation process with higher efficiency than the mill scale practices. So now in electric arc furnace, what happened that we require continuous supply of the oxygen, and modern electric arc furnace is okay using this particularly the uh, oxygen lensing system. Oxygen lensing system gives the enough and well calculated stoichiometry requirement oxygen that is supplied in the electric arc furnace, so that further oxidation of the metal is not happening. So that's why this utilization of the mill scale in electric arc furnace that is reduced. A small portion of mill scale has been utilized in cement plants. However, the mill scale does not uniformly blend with the other feedstock. The mill scale is not properly mixed, and then in steel plant, it fails. Okay, it doesn't give the proper result. At the same time, the amount of the mill scale used by the cement plants as a raw material in the manufacturing of clinker is still all very little. Okay, it's a very little utilization is there because it is not giving us the proper results. So these are the various can say utilization points of the mill scale. Okay, till now what we have seen that sludge and particularly the mill this sludge utilization points, but mill scale utilization there are different points are there, but none of them gives the proper result, and the results are mentioned over here. Okay, there are possibilities that we can utilize this mill scale in a different industries, but doesn't give the proper result. It is reported that the full-scale recycling of the mill scale is still difficult for many mill operators whose operations are without pre-reduction facilities. The mill scale is containing the nearly 40% to 50% iron oxide, and remaining is the different kind of oxides of the various metal. So it cannot be directly utilized. We need to reduce it. When we are trying to reduce it, the small scale industrial operators fail to do that because they are not having the pre-reduction facilities. In order to circumvent the capacity constraints of the recycling mill scale in mini mill operations, several investigations also focused on the utilization of the mill scale to produce the sponge iron. Okay, so research and studies are going on to produce this, particularly the reduce this mill scale and producing the sponge iron. Okay, on right hand side you can see that summary of the research. Mill scale is utilized by various researchers. You can see that with here that I have summarized this, but they have utilized a different flux. Reducing agent is a coke, temperature is 1050 to 1150. Reducing agent is low grade coal. Reducing agent is a carbon monoxide gas. Reducing agent is a wood charcoal. So different, you can say, flux they have tried, but the result is not so encouraging. These studies have shown that using the mill scale, it is possible to produce the highly metallized iron, producing with a chemical composition similar to the low carbon steel or direct melting in an electric arc furnace. Okay, that is possible, but it's again a very costly process. Then another is a pickling of the steel. When the steel is pickled, okay, pickling means the particularly steel is kept inside this particular the acidic environment for the certain time. Why? Because the final finish of the steel is required the different type of the treatment. So if you require the steel with the glowing surface or matte surface, you need to treat with the different acids. Now this steel, okay, that is kept inside the bath of the nitric acid, sulfuric acid or hydrochloric acid, okay, for the certain time duration in a sequence or maybe in parallel. Okay, and then you can have this metal surface that is treated. Now this treated metal surface is a finished product. Okay, so that whatever these acids are there, okay, after some time it is exhausted. Okay, because the salts are dissolved into the water, in the acid, and this acid needs to be treated. Now this paint acid requires different type of treatment, but at the end of this steel we require this acid treatment, we generated the sludge. So again we is generating the sludge over here at the end of the pickling. So pickling of the steel is one of the process which is again inevitable process. It is a must process and which generates the solid waste. So pickling is a metal surface treatment used to remove the impurities such as the stains, inorganic contaminants, rust or scale of the ferrous metals, copper and aluminum alloys, etc. Pickle acid reacts with the oxides and base metal to produce the dissolved metal salts, thereby neutralizing this particular acid. So metal salts are generated means the one of the solid material getting generated. The pickling process generates a considerable quantity of the spent pickle liquor, SPL, spent pickle liquor. Okay, spent pickle liquor is the SPL, containing the dissolved metal salts of the iron, chromium, copper, nickel, zinc, as well as the residual free acid. Now, carbon steel with an alloy content less than or equal to 6%, which is called the mild steel, are often pickled in hydrochloric acid or sulfuric acid. Steel with an alloy content greater than 6%, like stainless steel, must pickle with the two steps. Other acids are used such as the phosphoric acid, nitric acid, hydrofluoric acid, HF. Very dangerous acid. Okay, that is also required to be utilized. Rust and acid resistant chromium nickel acids are pickled with the bath of the hydrochloric and nitric acid. So you can see that all the different kind of steel require a different kind of acid bath, and this acid bath neutralized in particularly the this whatever the this oxide layer is there, and then finally the solid waste getting generated. The pickling waste generated in the steel is streamlined, that is shown in this particular figure. So suppose the steel rolling mill is there, okay, then passing to the pickling bath one, maybe two bath is required in bath two, and then finally the rinsing. So in rinsing we have the water bath. So whatever the acid content is there, that is properly washed off. Okay, so all the liquid, okay, after some time this acid bath and water bath, okay, sent to this particular neutralization plant. Okay, now being a chemical and environmental engineer, all of you know that in neutralization again the salt formation is there, because this is the acidic thing that is coming in. We are adding a certain base, maybe the limestone, and then neutralization takes place, and then sludge. So sludge is getting produced. Now when the sludge is getting produced, we need again the dispose of in a proper manner. Is another process by which formation of the spent acid and acid effluents. So it's a pickling process and rinsing process, and then we are going to generate this particularly the sludge. Existing common processes for the common spent acid treatment is the acid regeneration plant, effluent treatment plant, and then sell to the approved buyers. Okay, so what is to be done with this spent acid? Three things can be happen. One is the acid regeneration. Okay, so there are certain processes are available, okay, commercially, by which you can regenerate the acid, okay, from the spent acid, and then by regenerating acid like HCl, hydrochloric acid, where Fe is recovered and then it is sent for the further recycling purpose. But it's a very costly process. Okay, so many times what happened that in market the pure HCl available at very cheap rate, very commercially this hydrochloric acid, the rates are very low. So this recycling of the HCl or any other acid is very difficult, because commercially it is not viable. Technology is available, but commercially it is not viable. So ultimately it is sent to this particular effluent treatment plant. Okay, when effluent treatment plant is there, okay, usually it is neutralized with the alkali, lime or solids. Okay, and then whatever the sludge is there, that is disposed of in a secure landfill site, TSDF. Okay, water is reused for disposed as per the industry norms, okay, as per the ministry norms. And sometimes the third thing is that if some buyers are there, okay, they can take up this particular the spent sulfuric acid or spent nitric acid, okay, and then they can utilize it for the manufacturing of some utilization like ferrous sulfate, ferric chloride, oxalate, etc.
Then buyers are available, you can sell directly to there. Otherwise, if the buyers are not there, either you have to go for the regeneration or you have to go for the ATP. Now regeneration is commercially not viable, so you have to go for the ATP. So you can see that 90% of the industry going for the ATP, and then you can get this particular solid waste in terms of the sludge that is getting generated. So this is the acid regeneration process. Okay. Sometimes it is done by the anion replacement, sometimes it is done by the membrane technology. Okay, so various technologies are available, but the major issue with these technologies is what? High operating cost, high capital cost, and it requires the high volume also. For small scale industry, you cannot establish this acid regeneration. Okay, acid regeneration by the pyrolysis. This is one of the technology. This is acid regeneration by the anion displacement, and this is acid regeneration by the diffusion dialysis. But for all the three technologies, there are several disadvantages are there. For membrane, we have the service life issue. For anion replacement, we have the certain concentration is required. Means that less than 40% you cannot utilize. Otherwise, it is not commercially viable. So because of this issue, this AR process, the acid regeneration process, is not widely adopted. Now ETP, we have the pH adjustment, coagulation and flocculation, okay, then filtration, and then we can have the decantation, and then sludge production. So it's a very common process, but what to do with this sludge, it's a big problem. Okay, so here the research is required that if at all you can go for this ETP, then what is to be done with the sludge? If you directly dump into TSDF, it is also not free. It's also requires certain amount to dispose of. Now, this is some research-based studies taken up, okay, like industrial categories, the steel production, acid pickling, iron metal loss, paint acid effluent. What are the solid waste production, like large, medium, small, and total industry, okay. So based on these four categories, based on these three categories, large, medium, and small, okay, what are the various processes, what is the waste generated, okay. If you just simply look at the solid waste formation from the large industry, is 4050 tons per year, whereas in medium it is 27,000, and where in small it's 18,000. So total, I can say that waste generated by this steel industrial sector is very huge. Okay, it requires that particular the attention over here. You can see the large scale industries are afford to have the different technologies so that they can have producing the very less amount of the sludge or solid waste formation, whereas the medium and small scale producing the particularly the large amount of the solid waste. So here we require to focus. Okay, if at all any research you want to take up any faculty, then they can take up for this medium and small scale industry. Certain existing process issues with this particular industry, like ARP, that is the acid regeneration, ATP, and then selling of this particular the acid. Okay, these three technologies, three existing processes are there. Okay, then which are where you can find a significant concern. Okay, that is represented by this red color mark. Somewhat significant and favoring it, particularly the green color mark. Somewhat less significant with the red color, and somewhat less significant is by the green color mark. So you can observe that most of the time you will find the significant concerns with the ARP. Okay, same with the case with the ETP also. ETP, you are not having a much issues, but the major issue lies with the particularly the solid waste and wastewater. Now ETP, where to dispose of this solid waste and wastewater is going to be, because after treatment this water is also not of the recycling, cannot be easily recycled. Okay, so recyclability is lost for the water, and what is to be done with the solid waste is a big question mark. So is a percentage share by the various industries. Okay, large, medium, and small scale industries. Steel production around 70%, 20%, and 10%. So large industry produces the 70% of the steel, but you can see that the waste generation is very less. Okay, small industry generating the 10%, contributing 10% of the steel production. Medium is 20%, but their solid waste formation is tremendous. So that is what the difference of the automation and manual operation. Manual operation generates that's why I reiterated several times in this lecture that large scale industries afford the automation, they can afford the technology, produces the least quantity of the waste, whereas the small and medium scale industry is generating the large quantity of the waste. You can see the solid waste generation by this, particularly the large scale, that is a blue color, only 8.3%, small scale 36.7%, and medium 55%. You can see the percentage electricity consumption. Okay, so percentage electricity consumption by this large scale is 86%. Medium scale consumes 8% and 5% energy consumed by the small scale. So this SME sector, okay, contributes lot to this solid waste treatment, and that's why some research needs to be taken up. So this is the summary for the pickling waste and sludge treatment. Okay, the SPL treatment method depends upon its quantity, quality, and composition. Stainless steel methods is a safe landfill, sludge and scale method is safe landfill disposal method, but some sludge methods are economically valuable. So we have to not to dispose of, we have to recycle and reuse it. Metal compounds recovery depends upon its potential in a market, as they are costly methods. Okay, so recovery is possible, but it's very costly. So usually industries are not going for that. So that's why these industries are going for the neutralization, and that's why it's generating the most and most sludge. Now, what research we carried out, okay, for this particularly the steel sector, small and medium scale for the sludge and mill scale, let me highlight all here. And we try to recycle this particular sludge into the steel industry itself by reducing it into the proper formation, proper proportion of the iron and chromium and manganese. The research relates to the process for recovery and recycle of steel and stainless steel from the stainless steel oxides and sludge, okay, that we carried out. Many works reported earlier dealt with the direct reduction of recycling the mill scale, but no elaborate work in relation with the one-step direct reduction recycling of the mill scale plus mill sludge plus HTP sludge. All three together, okay, for the direct recycling is not carried out. Study and optimization of the parameters also carried out, okay, and what we observed, let me show you the protocol. We have followed these particular steps so that this mill scale and mill sludge can be directly analyzed. So mixing of the fluxes. Now this flux is again a different kind of chemicals we are adding up. Then waste stream and charging into the prototype. I will show you the photograph of the prototype. This is our prototype, which research we have carried out. In the furnace, we have kept this prototype, these small SS boxes, stainless steel boxes. So this sludge mixed with the flux and make a small molds that is kept inside the furnace. So drawing and cooling of the sample, the reduction in prototype at 1000 to 1200 degrees centigrade as per the patented process. So this kept inside this particular furnace, okay, at 1200 degree centigrade. Then we are taking up the sample, okay, and then going for the XRF analysis. Now this gives us the metal composition. Okay, so once we analyze it, we can identify that what is to be further added. Then we again put this particular material in the furnace at the 1600 degrees centigrade, okay, and then again carried out the XRF analysis, and then we carried out this energy consumption and all calculations, repeat the process, and then we have optimized this particular parameters. So this process carried out several times. So whatever the waste material is there, that is mixed with the flux, okay, waste stream plus flux, made these small balls, okay. In this particular SS box we kept inside the furnace, and then we have taken out, cooled down, and then we have measured several times this XRF analysis carried out, X-ray fluorescence, and then identified that SSDRS, particularly the stainless steel direct reduced iron that is produced. We have put it into the electric arc furnace. This electric arc furnace, very small scale electric arc furnace is there, and then finally melted DRI sample, that is a particular melted pig iron. Okay, so this is simply the iron as good as taken out from the blast furnace, same. So it is 100% recycled. So that study also carried out by us in with the help of the various industries, and we observed that this mill scale can be easily recycled. This particularly process gives that one sort of assurance that waste generation to this particular from this steel industry can be further reduced. This kind of research is not reported in the even literature, that this particular sludge can be recycled back into the steel industry itself by using this particular process. Now, this study we carried out for the mill scale. Okay, mill scale we have carried out. Now for the mill sludge, okay, the study in the same pattern we have carried out. Mill sludge is taken out from the filter press. We have made this particularly the small lumps of it, put it in the stainless steel box inside the furnace, heated into the 1600 degree centigrade. Yeah, here also we have added up the flux. Okay, sludge plus flux is there, and here we have the mill scale plus fluxes. So you can see the step over here, certain fluxes. Now flux is nothing but simply the different chemicals. It's a proprietary chemicals we utilized for the reduction of particular these oxides that is available in sludge as well as the mill scale. In mill sludge, we can put it again into the electric arc furnace, and then we identified that arc melted sample as good as particularly taken out from the blast furnace. So that kind of metal with around 95%, 95 to 97% iron that is produced from this sludge also. Then whatever the 95 97% iron sludge, this pig iron is produced from this mill sludge, this sample, okay, and this sample, that is further melted, okay, further reduced to have this pure iron. So mill scale and mill sludge reduced and heated to 1600 degrees centigrade to prove the concept of the one step process in 2 hours. So here this particularly the furnace is there. These are the balls of this particularly the sludge and particular slag, and then fluxes are also there. It's slowly heating up, taking up the heat. It's a conductive heat, can be observed over here. And then at the end we can see that by spark test, this is sparking test of this particular material we have checked. So pure metal only gives this kind of spark with a grinding machine. So this spark is observed. Even we have taken out this XRF and XRD analysis. It also gives this particularly the good or promising results. So research study which we carried out, okay, provides very promising results. Conclusion of our study that variation of the raw material properties, the patented technology shows the variation in the residual oxygen in a direct reduced iron. Based on the experience in the steel industry, when O2 exceeds to 0.5% in the feed material, it becomes difficult to melt. We observed, okay, so we recommended also that to the steel industry that they have to reduce this oxygen content so that the oxide layer on this particularly the steel can be reduced, and further less generation of the 3As, okay, that is a sludge, slag, and mini scale, okay, that can be reduced. We are trying to develop this single type reactor, okay, this is under process. Two-step process is already proven, but single step process we are trying to prove it. So in summary, what I can say that in conclusion, okay, that the need of the bench scale prototype which was demanded, okay, particularly that can be reduced. So here is a bench scale reactor, okay, which is there, which is further used for the sludge also. But here we need to go for the two-step process. The first step process over here, second step process is over here in both the thing. Now here this two-step process demanded over here that can be reduced to a single step also if the proper fluxes are introduced. So in one furnace only we can directly get from the scale and sludge directly get the final metal, reduced metal. That is what our target is, and studies are going on. So whatever demand is there, that is a two-step process is required. Instead of that, we can in the process to prove that one single step process is also sufficient. So what we expect, okay, this still the research is going on, that process time instead of 20 hours we reduce to 2 hours. Temperature 1200 that remains the same, and fluxes, okay, that we are going to add, that is also get reduced. But time which is consumed for 20 hours in a two-step process, we are in a research, we are under the research with the collaborative industry to reduce it into 2 hours. So the time is also saved. Now we save the time. You can understand that 1200 degrees centigrade for the 20 hours and 1200 centigrade for the 2 hours. How much energy is also get saved. And finally, we are going to get this particularly good, I can say, metal compound, okay, that is going directly recycled. So that research is going on. Hope we to get the research results soon in coming 6 to 8 months. So in summary of my talk today, I can summarize that waste generation from the steel industry is going to be increased tremendously due to increasing demand of the steel across the globe, not only for the developing nations, but developed nations also facing this particular issue. 3S, okay, 3S generated from the steel industry. These are three different kind of waste, okay, sludge, slag, and mini scale, okay, that's generated from the steel industry creates the major load on the environment, because these all 3S are the solid waste. 3S are the solid waste. Now for that, what we have to do, we have to employ the 3R: reduce, recycle, and reuse for the 3S. Okay, so whatsoever is applicable. So in this today's lecture, I just quickly gave you the different sort of utilization point, different sort of reduction points. Okay, then how we can reduce this waste generation, and then finally the research which is going on. So research for these three are also required, and the, some of the glimpses of the research which is carried out at uh, particularly by my students, okay, at our laboratory and also at one of the industry. It's a joint collaborative research that we try to prove certain concept, and we got a grant also from the government. So this is what the particularly at the end I would like to say thank you, and these are the certain references which is mentioned over there in some of the slides. Now I kept 15 minutes for the question and answer, so it's a 12:23. Okay, so 10 minutes are there. Okay, you can ask me the questions. Any participant, any questions are there? Hope you
Good afternoon,
got.
sir.
Yeah, good afternoon.
Yes, I have one question.
Yeah, please.
Sir, you have developed this one-stage reactor or two-stage reactor,
Yeah,
and
yeah.
how much cost it will require, sir,
See,
for treatment?
yeah. So costing part is depending upon two things. First is the energy part, and second is this. See, right now we are talking about the operating cost because the furnace is available with the industry, so we are working on that only. So two things, there is the energy part, and the second is this particularly the chemical part. Let me go back to this particular thing again. Yeah, comparison chart is there. No? Yeah, 20 hours and 2 hours. You can see. So two things are there. So 20 hours that is developed, okay, but tremendous energy consumption is there, and it requires a slow reactions. So here ultimately it's a simple reaction. By and large, we can say that it's oxides are there. We try to reduce it by in presence of certain chemicals, and these are the certain proprietary chemicals. We don't want to disclose it. It's again a patented one. So, but by using that chemicals, what happens that at high temperature at 20 hours, the recycling is done. So now, if you go for the cost wise, it's very costly. But at the same time, if you put the cost on the degradation of the environment, because if you want to bring in the environmental economics over here, then just dispose of in a TSDF site, okay, secure landfill sites, this particular waste, which is having the potential to recycle. No doubt it's very costly, but unnecessary, why to put over there? So that is a very important concept. So you rightly pointed out that the steel produced from the two-stage process is very costly compared to the readily available steel from the or I can say commercial process like making the steel from the ore, okay, conventional process. So that is not usually attracting the industrialist to adopt. Okay, and that's why we have taken up this particular process into this second step, that why can't we go for this particular the one step only and remove all sort of hindrance. Okay, so this additional machinery, that is for example the steel chambers where we have to put this material, again additional furnace directly in this furnace, the second layer, whatever the furnace is there which you can observe, in that furnace only we have added all the, you can say, fluxes and the raw material. So we got failure, but we have modified the particular the fluxes, means the chemicals, and we are getting some of the success. So here this is not 100% success, so I cannot comment on the costing part. But if I am confident, I'm confident that if this is going to be success, no doubt the costly chemicals to be utilized. That is for sure. But energy consumption is going to reduce dramatically, 20 hours to 2 hours. Okay, that too at the 1200 degrees centigrade. So the dramatic reduction in the energy consumption will make the process economically viable. So this costing wise, okay, this process is somewhat costly with the conventional one, but this after experimentation we are sure that it can reach to the or meet the expectation of the industry to make the cost effective process. Hope I have answered your question.
Okay. Yes. Thank you so much.
Yeah. Any further questions?
Hello,
Still
sir.
yeah.
Am I audible?
Yeah. Please go ahead.
Sir, I'm Dr. Shweta from MIT
Yeah.
University.
Yeah, madam.
So it was very nicely presented and very detailed. I come to know about the steel industries and different waste and what is their solution and what are the lacking factor on which work can be done. So it was very good to know about that. So my question is there any bioleaching based approaches which is developed to absorb matters from the leachate before dumping it into the landfill area?
Bio means you want to have this fungus and bacteria. I mean, dead fungus and bacterial biomass kind of research
Yeah.
you are. Yeah. Okay. Yeah. So as far as I came across all the literature, probably I couldn't find much over there. Okay, that because what happened that here this biomass utilized for the minimum quantity. I mean, this leachate contains the very minute quantity of this waste material. I mean, the metals. Okay, here the metals, particularly even in leachate also of high particular amount. Okay, high concentration is there. I think I have not come across any literature for that. If you want to
Yeah.
take up this research in this direction, that is really a good thing. You can take up.
Okay, sir. Okay. And sir, you told us about the moist dust-laden gases which is leased. So I
Yeah.
would like to know about the gases and is there any filtration process which is used by these industries to
Yeah.
filter those gases?
Yeah, madam. Usually in steel industry, what they will do, because see, it whatever the fluxes are added, okay, in this particularly the furnaces, along with that certain gases, carbon dioxide, monoxide, it is done again with certain water. The moisture is that it goes away with this particular air stream. Okay, now that
Yeah.
first pass through this cyclone separator. Okay, then bake filters and then electrostatic precipitators. So these are the,
Okay.
yeah, no doubt they are going to control air pollution control measures are there, but we can say that these are the air pollution probably going to be occur, but measures are there. Okay, but at
Okay.
the end of the electrostatic precipitators, usually will not find anything. Sometimes I have seen in the chemical industry they are using the scrubbers. In one of the steel industry, I have suggested to utilize it, but they are not utilizing these scrubbers, or because in second furnace when they are utilizing, okay, sometimes these acidic fumes are there, which is observed at the end of the electrostatic precipitator, because you know very well that acidic fumes when pass through the cyclone or bake filters or electrostatic precipitator, it is not going to be captured, it is goes away. So
Okay.
sometimes it is required to use the scrubbers also.
Okay. So one more question.
Yeah,
May I
madam.
ask?
Yeah.
Yeah. So one question is, I come to know about the waste material cinder, which is coming out from the furnaces, and that is used to grow the plants.
Yeah.
So is it safe to use cinder to grow the
No,
plants?
no, 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 no. If you look at that slide very carefully, and I think I have explained clearly, but somehow probably you missed out that part.
Okay.
Let me show you again. Yeah, this one, soil conditioner. Okay, at that time I told very clearly that chromium should not be present. The rest of the thing, okay, like silica, calcium, manganese, iron, calcium, okay, all will work as a micronutrient. Okay,
Okay.
so you have to go for this particularly XRD, XRF elemental analysis for the slag, okay, before utilizing as a soil conditioner or fertilizer. Okay, if none of the heavy metals are present, then and then you have to go for this. Otherwise, you can't.
Okay. Okay.
Yeah.
Okay, sir. Thank you, sir.
Okay. Any other question? Okay. Sorry.
Sir, can I ask one question?
Yeah, sure.
Sir, can we use foam separation techniques for the treatment of these effluents?
Can you elaborate? What do you mean by foam separation technology?
By making use of surfactants and.
But madam, see, these surfactants and things used for when the oil and grease is there. Okay. Here the main issue with this wastewater is simply the heavy metals. Okay, and heavy metals, the conventional biological treatment also fails. And when the conventional biological treatment fails, you have to go for physicochemical treatment. The physicochemical treatment, nothing but simply the neutralization and then precipitation. When you precipitate out, you have to require the filtration. When you filter it, the solid sludge separates, water separates. Now, what to be done with the solid separation, separated solid sludge? That is a major issue.
Okay. Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Okay. So, shall I leave? No more further questions?
Any questions?
Participants can ask any question.
Yeah.
Sir, I had called you right in the beginning.
Yeah.
Sir, one question.
Myself, Nana.
Yeah, madam. How are you?
Yes, sir. Thank you, sir. Thank you for being with us and accepted our invitation.
Yeah, thank you, Professor Vaghela and entire team. Okay, for inviting me to deliver this lecture. So we have completed on time, 12:33. So shall I exit, or any further formalities are there?
Piyush sir, conclude the session.
Yes, sir. Yes, sir. Thank you very much, sir, for such a nice session. And today that you have discussed about that a case study related to steel industries that is very useful to us, and that participants are also very interested that in your presentation. So it was such a very nice session. Thank you very much, sir, for your presence here. Thank you, sir.
Thank you.
Okay. Thank you very much, sir.
Goodbye.
Okay. So we can conclude the session. So participants, you can leave now. Next session is at 1:30.